Xiaoqi Huang from Louisiana State University, who will speak about eigenfunction and spectral projection estimates on hyperbolic surfaces.
Thanks, introduction, and thanks organizers for inviting me. So today let's first discuss settings. We will first discuss some more general setting and then talk about the results on hyperbolic surfaces. So we are mainly interested in compact Riemannian manifold without boundary of dimension bigger than 2. And we are interested in the eigenfunctions of the Laplace spectrum operator. So it is in the compact case, it's a self-adjoint operator with a discrete spectrum. And our notation is so lambda is the eigenvalue of the square root of the Laplacian, same as Simon's talk. And we assume the eigenfunction is L2 normalized, and the notation for eigenfunction is E lambda. And the other notation we use we use the indicator function P, where P is the square root of negative Laplacian to denote the spectrum projection operator for intervals of lambda to lambda plus delta. And so this acting on a function f is a linear combination of eigenfunctions with eigenvalues in this interval, and with the coefficient coming from inner product. So we are mainly interested in the LQ norm of eigenfunctions, and so this is kind of the discrete free restriction problems in the manifold case, and also for possible applications into PDEs and to study the equations like wave and Schrödinger. And we are interested in how does the LP norm depend on the geometric properties of the manifold. So in the sphere, there is an explicit expression for the spectrum, and there is what's the examples in the case of sphere. First is Sonor functions, where the LQ norm of Sonor functions is approximately lambda to this power for q bigger than 2 over n minus 1 and also equals to 1 otherwise. So the Sonor function, the expression involves the Legendre functions, and it's complicated, but the other range is highest-rate spherical harmonics. So if we allow complex valued eigenfunctions, it has a simple form. That is x1 plus ix2 to the power of k, and the highest-rate spherical harmonics has a LQ norm approximately equal to lambda to the n minus 1 over 2, 1/2 minus 1 over q, for any q bigger than 2. And here is a rough picture where Sonor function takes large values near a point, and the highest-rate spherical harmonics takes large values near geodesics. And so it is an earlier work of Salk in 1988, saying that not only for eigenfunctions, but for linear combinations of eigenfunctions in a unit interval, the spectrum projection operator acting on F has LQ norm bounded by lambda to some power L2 norm of F, and for large lambda. And so here the two powers are the maximal between these two numbers, coming from which is the same number as Sonor functions and highest-rate spherical harmonics. And so in different range, they dominate in different ranges. So and these two numbers equal as the exponent 2n plus 1 over n minus 1, which we often call the critical exponent. And so some remark is like first the sigma q is better than the n times 1/2 minus 1 over q in both ranges. This is a Sobolev estimate bound, and it holds more generally for eigenfunctions in dyadic intervals instead of unit intervals. And So power on lambda is sharp on any smooth compact manifold. So in the case of sphere, there is a saturation example that is given by eigenfunctions. But if we allow combinations of eigenfunctions like quasi-mode, this power cannot be improved on a compact manifold. And this is also related to the fact that this is essentially a local operator that does not see the global properties of the manifold. And so the question is like to have a better study of eigenfunctions, we want to shrink the size of intervals. For intervals smaller than size smaller than 1, we wish to obtain improved LQ bounds, where we hope there is a gain of epsilon to some positive power compared with the standard unit interval spectrum projection estimates. And so an example of this is in the non-compact the Euclidean spaces, the Stan-Thomas restriction theorem says for QC, the critical exponent in the previous slides, we have a gain of square root of epsilon for depending on the size of the interval. And so for Q bigger than QC, this is proved by Thomas, and the endpoint is solved by Stan subsequently. And so the spectrum projection operator in the Euclidean case has an explicit form. It's a Fourier restriction to the annuals of with epsilon. And also, for Q bigger than QC, square root of epsilon is best power one can expect. If you have some power better than this, you will get certain, like for example, improved Sobolev estimates if you add these intervals to a dyadic intervals by Cauchy-Schwarz. So this is sharp for in terms of the gain in epsilon. And so on compact manifold, first of all, we do not have cannot let epsilon goes to 0 compared with a non-compact case due to the eigenfunctions of course have LQ non-bounded below by 1. And in particular, for instance, if M equals to the sphere, the best we can hope is there is no gain in terms of epsilon at all if lambda happens to be the eigenvalues of the Laplacian. And so on the sphere, for instance, if lambda equals the square root of the k times k plus n minus 1, the spectrum of Laplacian, then the projection operator of epsilon window is equal to the kind of essentially equal to a unit interval. So the question is like for smaller intervals and for manifolds that is other than a sphere, what can we have and what is the best powers of epsilon we can have? So I will state some results in this direction. So for this slide, we will talk about the case where epsilon equals to 1 over log lambda. So we call it logarithmic intervals, the spectrum projection operator. So in the earlier work of Girard in 1977, he obtained improved spectrum projection estimates for manifold with non-positive curvature. And for saying for P equals to L infinity, a gain of square root of epsilon is obtained compared with uniform estimates. And so this is in the same work, this is in this also obtained, for instance, improved while remainder estimates for the counting function using a similar argument. And so this is kind of also influential on our work. So Girard started using the Harleman parametrics in the setting of non-positive curvature and analyze the growth of, for instance, coefficients in the Harleman parametrics, and to study this spectrum projection operator and obtained this, which is also used later in our work. And for Q bigger than QC, so bigger than the critical exponent, this was later generalized to Hassel and Tacey in 2012 for the same epsilon and for the same conditions, that is non-positive sectional curvature, and obtained gain of square root of epsilon for any Q bigger than QC. And later it is Bolzano in 2017 kind of generalized this non-positive curvature condition to the manifold without conjugate points. And there is also latest sequence of works by Konsania and Golkowski that further weakens conditions, that is on the certain dynamic assumptions weaker than the no conjugate point, and obtains square root of epsilon gain when epsilon equals to 1 over log lambda. And there is also the story about the Q less than the critical exponent. And in earlier work of Sog and Seldage, they considered, I think, 2 dimensions and obtained the some L4 norm estimates with improvement of little o compared with big O lambda to the power. And there is subsequent work that I cannot list all of them, but the works by Blair and Sog and also so they consider the kind of the improved estimates for epsilon equals 1 over lambda, and to get some partial result in terms of the gain for Q smaller than QC. And so there is also a result, for instance, in the setting of manifold with less non-smooth matrix and the manifold with boundary. There is also a history of spectrum projection estimates, but we will not discuss today. And so in a recent work with Sog, we showed that for n-dimensional compact Riemannian manifold without boundary, assume the sectional curvatures are negative. Then for lambda bigger than 1, we have the uniform bound that for logarithmic intervals, we have a gain of 1 over square root of log lambda for any Q between 2 and QC. So here, in terms of the gain, 1 over square root of log lambda, it can be shown it's sharp because it is possible to add up the estimates for logarithmic intervals to imply the unit interval estimates. And we know the unit interval estimate is sharp on any content manifold. And so the size of the 1 over log lambda intervals we consider is also limited by the error-free time. So this is a time scale that many of the tools in our analysis fails. And so later today, I will discuss 2 cases where we try to break the barrier, like to consider small epsilons, but for a certain specific class of hyperbolic surfaces. And so there is also the condition that is negative curvature. So in terms of the lower bound on the upper bound on the curvature, so it is necessary. In the same work, we also showed that, for instance, if we are on the torus, 0 curvature, in terms of the gain in the size of the interval, on torus, there exists explicit examples that the gain is 1 over some smaller power than 1 over 2. So there is a so-called discrete NAP example. So so non-positive curvature is not enough compared with earlier works in the previous slides. And So let's also compare with the Euclidean case. In the Euclidean case, the Stan-Thomas restriction theorem for Q between 2 and QC, if you interpret, you will get 6 power. So at QC, this is 1/2. And at 2, this is 0. This is the power coming from interpolations. And the proof is by writing out the inverse Fourier transform explicitly and study the restriction operator. So, actually, the interpolation between 2 and QC is the best power we can get. So there is so-called NAP example that shows that this estimate is sharp for Q between 2 and QC. And so the NAP example is a function that has a Fourier transform live in a rectangle. And this is kind of the biggest rectangle that can live within an annulus of with delta. And if we compute the powers, delta to this power is kind of slightly worse than in terms of the gain, than the delta 1/2. So we can roughly say that the spectrum projection estimate in the negative curvature case is better than the Euclidean case. And this is kind of related to the Queen-Stan phenomena. So where they studied the convolution operators on Lie groups, such as hyperbolic spaces. And they find it's easier for convolution operator to be LP to LP bounded compared with the Euclidean space. So we'll also come back to this later. So let's first briefly describe the strategies in the proof of spectrum projection estimates. So we often replace it by unit interval. We smoothed out a version of the spectrum projection estimates. And we use a notation T to be equal to delta to 1/2. And then T is kind of equivalent to the propagation time. And the smoothed out version of the projection operator shares similar properties with the unit interval spectrum projection operator. And it's kind of much convenient in the explicit analysis. So for instance, when delta equals to 1, try to get the universal estimates of solved in 1988. We can use the inverse Fourier transform to rewrite the spectrum projection operator as an average of the half-wave operator with some function. And if we first assume rewrite it as we can further rewrite it as average of the solution to the wave equation plus some negligible error. And so the error term this is kind of a smooth symbol that has a rapid decay in lambda. And this term is often treated using Sobolev estimates, which is enough. And often we impose the assumption that rho hat T is supported in a small time interval, such that for the small time scales, it is possible to write down the parametric constructions for the solution to the wave equation. After we plug in the parametric constructions and compute the DT integral, it is possible to reduce the kernel of the spectrum projection operator into a oscillatory integral operator like this. And so this is a kind of a variable coefficient oscillatory integral operator with the phase function that is a distance function of the Riemannian distance function. So at this stage, for instance, if we want to get L infinity estimates, we already have the L infinity estimates coming from the coefficient. This is coming from the station phase calculations. And if we want to get LQ estimates for the critical exponent, we invoke the oscillatory integral operator, LQ estimates for oscillatory integral operators if the phase function satisfies the Caristen-Julin condition, we can apply the ordinary integral theorems. And so this is one of the proof of the unit interval spectrum projection estimates. And there can be other approaches, like for instance, there is a paper of Koch, Tataru, and Xiaoqi, the semi-classical LP eigenfunction estimates. In such sense, the L infinity estimates become certain energy estimates of the variable coefficient equation PDEs, and the LQC estimates becomes some semi-classical LQ Stukas estimates. But one of the advantage of using this approach is the solution for the wave equation kind of have some expression in the setting of non-positive curvatures, and it also has a finite propagation speed. So let's say if delta is smaller than 1, if we follow the same strategy, it will be the spectrum projection operator will be average of much larger time scale, that is time scale t equals to delta to the negative. And so we will need a parametric construction for the solution to the wave equation for large time t, at least, for instance, logarithmic times. And so for one of the approaches, if the manifold has a covering manifold, the solution can be related to the solutions on the covering manifold. That is, we can extend the solution in a fundamental domain periodically. So this is this will become the kind of a relation between solution on the for the wave equation on the covering manifold and the solution to the wave equation on the compact manifold. So the thing is, in the non-positive curvature case, by a theorem of Kadan and Hadamard, this is where we use the curvature assumption. So the covering manifold can be defined through the exponential map, in the sense that the covering manifold is like Rn, and it has equipped with a matrix that has non-positive sectional curvature. So this manifold has like no conjugate points. So we can kind of write down the solution to the wave equation explicitly for large time t. And also the other places we use non-positive curvature is like it will guarantee some nice estimates about the coefficients of the Hadamard pi matrix for the solution to the wave equation on the covering manifold, because the coefficients often depend on the some property like a determinant of the matrix inverse, and by certain like comparison theorems for the matrix, and it is possible with a non-positive curvature assumption to get control on the size of the coefficient. So if we follow this strategy for the large time case, as in the previous steps, after we plug in the pi matrix, it will be essentially become some sum of many oscillating integral operators. And here the sum is alpha in the group of deck transformations. And each one is oscillating integral in the similar form with so the distance function by the finite propagation speed of the wave equation, the distance between x and translated copies of alpha y should be less than t. And due to the finite propagation speed. However, we can the number of the such choices of alpha. So it's kind of like the number of fundamental domains within in the covering manifold within radius t of a fixed point grows exponentially due to the negative curvature. And so if we estimate each of the single term like before, and add it up, like using triangle equality, this will be painful, and especially when t is close to the logarithmic scale, there will be a loss of powers of lambda. And to get estimates for the small intervals, one of the strategies is we use height decomposition to divide the spectrum projection operator into small values and large values. So here, what we need is for the large value set, where the function is bounded below, what we need is it is bounded below by the size of the Gaussian beams. So this is the L infinity norm of the Gaussian beams. And in the large height set, we try to eliminate the geodesic type concentration. And with this lower bound, it will be easier to estimate this set, for instance, for small exponent Q. And for the set A minus that has an upper bound on the value of the function, we essentially require this upper bound is better than the L infinite norm of Sono function, that is better than n minus 1 over 2. So with this upper bound assumption, it will kind of eliminate the pointwise concentration of any functions, and this will kind of make the proof of the estimates for Q bigger than QC much easier by in this range. So so on the set of A plus, the main enemy is point concentration, and on the set of A minus, the main enemy is geodesic concentration. So on the set of A plus, our approach is kind of similar to the earlier works of Hazeltesi and later. So we use a TT star argument to try to rewrite the spectrum projection operator as a average of as a half-wave operator. And we write it as a local part and a global part, where the local part is average. We want to average only takes unit times in this average, that is negative 1 to 1. And a global part, which is a part of the time that is bigger than 1. So the local operator can be treated using the low estimates, and by finite propagation speed, it does not rely on the geometry of the manifold. And additionally, for the local part, we have a gain of 1 over t because of the long-term average. So we automatically gain a 1 over t for the local part, and argue as before, we can get the estimates. For the global part, so one of the this is also like one of the main ingredients when people trying to prove like improved wild remainder or improved LQ estimates for Q bigger than QC. We have a kind of the pointwise bound for the global operator. So so this is like the lambda n minus 1 over 2. This is a coefficient in the Austrian equals we write in the previous slides, and this coming from the number of different terms in the summation. So this hold, this is one of the places. This hold on manifold of the non-positive curvature, and or possibly it's try to generalize to a manifold with no conjugate points. This also hold. And so to handle the G lambda operator, we use the fact that the lambda times the exponential in t will be smaller than the square of the lower bound. This is the lower bound for the A plus set. So it will be less than the square of the lower bound if t is chosen small enough. For instance, we can choose t to be a very small constant compared with sigma here, and we will have this bound. And yes, this is kind of, we try to use a bootstrap argument to control these global operators. Because this is less than the lower bound of the set, we can absorb it to the left-hand side when controlling it. And this is related earlier works, ideas in earlier works of Bourgain and Salk, and the pointwise estimate is related to the ideas in the work of Hansel and Casey. So this is main ideas of trying to control the LQ estimates for the set which it has a lower bound, and where the point concentration dominates. And for the set where it has an upper bound, set has a ceiling, we need to use a more harmonic analysis. So we use Q-News pseudo-differential operators with frequency supported in a very small window of a given vector. So this is restricts directions to a small neighborhood of the fixed covector, and so this gives a directional localization, and the spectrum projection operator itself localized to annulus of width epsilon. This kind of localized in the height. So these two together composition is kind of similar to a wave packet in the Euclidean space harmonic analysis. And so if we chose phi properly like lambda 1/8 separated on the set of directions, the support of the pseudo-differential operators will be essentially disjoint. So they satisfy, for instance, Prandtl type theorems like they are L2 orthogonal. And so 1/8, this is, there is some flexibility here. This is related to the value of sigma in the previous slide. So as long as it is chosen kind of correspondingly, depending on the size of sigma, it can be any number between the 0 to 1/2. And beta and beta tilde are the smooth functions. So the pseudo-differential operators on compact manifold is defined in local coordinates. And on compact manifold is there is finitely many pieces, so it is possible to reduce the calculations into a fixed local coordinates and do the explicit calculation. So on the set A minus, the main step is to show the following almost orthogonal type inequality, saying that the LQ norm for Q smaller than QC is less than the little LQ norm of the sum of the localized pieces plus good error. And by good error, I mean there is a gain that is in the power of lambda compared with the logarithmic gain. So this is based on writing raise the spectrum projection function to the square and expand it as a bilinear sum in terms of the pseudo-differential operators. And right here, organize the sum in terms of the broad part and a narrow part. The set where nu and nu prime is closed, we often call it a narrow part. And when nu and nu prime is large, we use call it a broad part. So for the broad part in the harmonic analysis, we often use bilinear and multilinear estimates. And for the narrow part, we treat it differently on the different context. So, for instance, when Q equals to 2n plus 2 over n, this is a bilinear exponent. This follows from applying results of Lee in 2006, so which is variable coefficient functions of the bilinear estimates of tau, Vegas, and Vega, and related works when they studied bilinear restriction problems in the Euclidean spaces. And in dimension 2, the proof of the bilinear estimates is relatively much shorter, and it follows from earlier works of Homander in 1973. And after the work of Lee in the 2010s, Sorg and Blair kind of adapted this Austrian integral estimates, bilinear Austrian integral estimate, to the study of the spectrum projection operators. And so we also want to emphasize that this estimates on this page does not depend on the geometry of the manifold. As long as we have a upper bound on the height, it is possible to prove such almost orthogonal type inequalities for Q smaller than QC. And additionally, for Q strictly smaller than QC, like Q not equals QC, we even don't require the upper bound on the height. The bilinear estimate is sufficient to get us gains in terms of non-trivial powers gains in terms of lambda. So the only places we require the upper bound on the height is a critical exponent. And later today we will discuss the application of this to the arithmetic settings for hyperbolic surfaces. So, so with the Q-new operator, we want to treat analyze the first term on the right-hand side. And with the additional Q-new operator, on the kernel side, it has the effort of trying to reduce the number of deck transformations from exponentially many to only linearly many in terms of t. So this is only hold for t smaller than a constant times log lambda. For large t, it will still grow exponentially. And so this is kind of essentially saying that along a given directions, if you travel along a different directions on the covering manifold, as long as the neighborhood of the direction is small enough, you will not see as many of the fundamental domain as in the arbitrary direction case. You will not see the foreign growth. And this is a kind of observation in the earlier work of Sorg and Blair in their orthogonal comparison paper they used to study the LQ number of eigenfunctions for Q smaller than QC. And with this, it is possible to analyze the first term on the right-hand side with some additional analysis. So now the thing is, let's discuss some examples of manifolds that delta can be smaller than 1 over log lambda. And the first example is a hyperbolic manifold, the hyperbolic space without any quotient. So it follows from earlier work of Huang and Xiao in 2014, saying for Q between 2 and QC, actually for any Q between bigger than 2 and infinity, we have a gain of square root of delta in the spectrum projection estimates for arbitrary small delta. So this is kind of not surprising that we have an explicit expression in terms of for instance, the spectral measure on the hyperbolic manifold. And so there can be, the calculations can be carried out explicitly, and there is no quotient, and so there is no summing of the different deck transformations. And Chen and Hassel generalize the cis to the non-trapping asymptotic hyperbolic manifold. So for high frequencies lambda, we don't need assumptions as on the bottom of the spectrum, and it also hold the same result hold. And so by non-trapping, this is also mentioned in Zhongkai's talk. So it means geodesic will escape to infinity, at least in one of the directions. And so in terms of manifold with trapping, so in the work of Han, Xiaoqi Han, he considered convex co-compact hyperbolic quotient that has assumptions that the Hausdorff dimension has of the limit set has some assumption. So this is kind of the analog of the pressure condition in the variable curvature case. And with this pressure condition, he showed that the same estimates hold for this type of hyperbolic quotient for arbitrary small delta. And in dimension 2, for hyperbolic surfaces, recent work of Anker, Germain, and Tristan Legger, they also considered complex hyperbolic surfaces. And they obtained the same result with a curvature assumption and with a pressure condition. And for any convex co-compact hyperbolic surface without curvature assumption, they proved the these estimates with additional epsilon loss.
It's not the same delta.
Yeah. Oh, yeah, this two delta is not the same delta. Thanks. So in the recent joint work with Zhongkai Tao and Zhexin Zhang, we showed that for asymptotic hyperbolic surfaces with negative curvature, the sharp spectrum projection estimates hold for lambda, for high frequencies lambda, and for delta that is arbitrarily small. So this class contains convex co-compact hyperbolic surfaces without assumption on the limit set, or the pressure condition, and we kind of remove the lambda epsilon loss in the Germain, Anker, and Tristan's work, and also to the variable curvature case. And in terms of the if delta equals to 1 over logarithmic lambda, this result is possible to generalize to high dimensions. Following the approach of the compact manifold case, we can extend the logarithmic interval result to the manifold with bounded geometry or negative curvature and the negative curvature. So this kind of has no assumption on the infinite end of the hyperbolic surface. So manifold of bounded geometry, you can think of it as a covering manifold of the compact hyperbolic spaces. So it is kind of periodically the same pieces when it goes to infinity. And so this is in a different language. This is equivalent to the LQ prime to LQ estimates for the spectral measure for the square root of the negative Laplacian, and kind of saying that the spectral measure is LQ prime to LQ bounded with lambda to the twice of the power. And so this is also hold for Q bigger than 2 and less than infinity. So the Queen-Stein phenomena we discussed previously is saying that the spectral measure for on the hyperbolic spaces is easier to be LQ to LQ prime bounded than the Euclidean spaces. So in Euclidean spaces, this is only hold for Q bigger than critical exponent. It does not hold for any Q bigger than 2. And such estimates also have applications like in the PDE analysis or it has application to the, for instance, global streetcast estimates for high frequencies for the wave equation and things like this. And so here is an example of a convex hyperbolic manifold. In the infinite end is a final end and looks like hyperbolic. In the convex compact region, it may have periodic geodesics, and when geodesic enters the compact region, it may be trapped. So let's briefly describe the proof. In the follows from earlier the paper of Bugan Diatlov in the spectrum gap paper, they showed that a consequence of it, as discussed in Zhongkai's talk, is the cutoff resolvent estimates or local energy decay. If we say that if we localize onto a compact set on both sides of the resolvent operator, we can get we have it is L2 to L2 bounded, no matter how small is the imaginary part. And if we don't have the cutoff, this does not hold, and the only approach is probably the spectrum theory. But so equivalent version of the resolvent cutoff resolvent estimates is local smoothing estimates for Schrödinger equations with logarithmic loss. So these two are essentially the same by using a DD star argument and rewrite the resolvent using an integral of Schrödinger solutions. And the local smoothing estimates is used. This is another paper that is influential on our work. In the work Guillermo and Hassel in 2010, they proved kind of the streetcast estimates on intervals of size lambda -1 times logarithmic lambda, and they combine it with the local smoothing estimates to obtain certain no-loss streetcast estimates on unit intervals for the solution to a Schrödinger equation for a class of asymptotic hyperbolic manifold with trapping and with a pressure condition. And this is now kind of related to the earlier argument in the PDE community, trying to use a local smoothing estimate to upgrade the small interval estimates to the unit scales in the non-trapping setting. But Guillermo and Hassel, they adapt this argument to the logarithmic intervals. And so the natural question is, we are kind of in a similar setting. We have a logarithmic interval spectrum projection estimates. Can we somehow upgrade it to the much smaller interval estimate following a similar approach? And I also want to mention that in the same work, we also consider the streetcast estimates for the Schrödinger equation and obtain some global in-time estimates for high frequencies in terms of the this is what we do. Like assume the manifold is a union of a trapped region and a non-trapping region, and so we construct the some ancillary manifold that is or so-called background manifold, such that it agrees with the manifold on the infinite end or the non-trapping region, and we modify the trapped region to some nice with some nice hyperbolic matrix, so that the whole manifold becomes have the nice property like a negative curvature and simply connected, and so it has the favorable spectrum projection estimates. And more explicitly, if we use chi to be a cutoff function to the neighborhood of a trapped set, and we use chi infinity to denote the cutoff function to the infinite end or non-trapping region. To study the spectrum projection operator, in order to try to adapt the local smoothing estimates in the Schrödinger formulation. We can also fill it as we can also choose a smooth projection operator related to the Schrödinger to the Laplacian without a square root, and write it as an average of the Schrödinger solutions. And if it is frequency localized, the Schrödinger solution also have like a semi-classical finite propagation speed related to the finite propagation speed of the wave equation. So this is possible to carry out in the analysis. So it suffices to prove the projection estimates for the non-trapping region and the trapped region. So on the non-trapping region, this is the strategy in the similar strategy in the Strikas estimates argument. In the non-trapping region, if phi equals to the cutoff function times the solution to the Schrödinger equation, phi will solve inhomogeneous Schrödinger equation with an inhomogeneous term coming from the commutator of the cutoff function with the Laplacian. And so it is possible to write out the solution as a homogeneous solution of the on the Anchovy manifold with a Duhamel term involving the Anchovy Schrödinger propagator and the commutator. So for the non-trapping region, the strategy is if we plug this expression into the previous slides, the spectrum projection operator localized to the non-trapping region will be the first term will contribute to the first term. The cutoff function will localize to the right-hand side, and we can apply the sharp spectrum projection estimates in the good setting or in the manifold without trapping to these estimates, and this is follows from, for instance, earlier work of Chen and Hassel in the setting of a non-trapping case. And for the Duhamel's term, it amounts to try to treat the commutator term using the application of local smoothing estimates, L2 to L2 estimates, to kill the one derivative coming from the commutators. The strategy is to apply the local smoothing twice in this formulation, and somehow adapt it to the setting of L2 to LQ type estimates. And so for the trapped region, this is the main argument is we try to localize it to the time intervals of size lambda -1 times log lambda for the Schrödinger solutions. So this is a scale that we know how to do the spectrum projection estimates. And by Cauchy-Schwarz inequality, we can fill the spectrum projection operator on the compiled region as a little L2 sum of the solution to the of a little L2 sum of time average of Schrödinger solutions on logarithmic intervals times some loss. And the thing is, we kind of know how to estimate each of these terms in terms of L2 to LQ estimates for average over logarithmic intervals using the strategies in the spectrum projection estimates for compiled manifold. And we follow the approach that is in the previous slides, try to use treat the Duhamel terms coming from because of the localization in time and because of the cutoff. Try to treat the Duhamel terms using the local smoothing estimates of the Schrödinger equation. And so this is main strategies in the proof of this. And so in the end, I want to discuss another recent ongoing work. With my collaborator Xiaoqi Huang. So we are interested in the arithmetic hyperbolic surfaces. So recall that the argument we use for the low height, for the set with an upper bound on the height, it does not depend on the geometry of the manifold. And for instance, in the arithmetic hyperbolic surfaces, the eigenfunctions of the Heck and mass operator already have a L infinity norm in terms of the upper bound. So due to the result of Sanak and Ifanic, that is better than the lambda to the 1/2. So it's 5/24. So we automatically have a L infinity norm gain. So we try to apply this machinery, and it will to get some improved LP estimates for the arithmetic eigenfunctions, especially for the critical exponent, because it will not follow from interpolation with L infinity estimates. And we are reduced to a task of trying to estimate this norm, where we replace this rho lambda f by the arithmetic eigenfunctions. And so this is we try to compute it using the method of arithmetic amplification used in the earlier works of Sanak, Ifanic, and later by generalized to the geodesic restriction problems by Simon Marshall, and to the study of micro-localized LQ norm of eigenfunctions, and try to use additional information coming from the micro-localized operators to improve the counting process in the arithmetic amplification process. And we have some partial result in terms of the gain in the LQ norm, especially LQC norm of eigenfunctions in the arithmetic case. And but in the general setting of compact hyperbolic manifold, our hyperbolic surface is still quite open, where we can get lambda, even a lambda epsilon improvement for the compared with the general case for eigenfunctions on the negative curved spaces. So I will stop here, and thanks for the attention.
Thank you very much. Questions, comments?
Yeah, you just come back to the estimate in the compact case for the A plus sets. So you have this G lambda of xy. And I just wanted to handle to handle these bounds. Do you have like explicit bounds on the Schwarz kernel of the half-wave semi-group e to the ITP xy, or do you use three-card estimate? Like, how do you use bounds?
Yeah, so in the study of global time problems, we often replace it by a wave propagator, cosine TP. And because this one does not have finite propagation speed, or unless we module smooth terms. But for the wave propagator, we use a Harleman parametrics for the wave propagator, cosine TP, up to the logarithmic times, and we have this bound after averaging in time. So we use the parametrics for the cosine TP, and we use the finite propagation speed to count the number of different deck terms.
Questions?
A question. At some point, you said that one of the bounds you obtained on hyperbolic surfaces or manifolds was sharp. On logarithmic scale interval.
Yeah.
So how do you show? So do you construct a quasi-mode which has this?
Yes, this is, we hope to construct a quasi-mode, and we're still not done yet. But the sharpness of this is like by contradiction. So it is possible to use this logarithmic interval spectrum projection estimates to imply the unity interval spectrum projection estimates by just kind of add it up using the Cauchy-Schwarz inequality. So if this is something better than log lambda, like log lambda to the -1, it will imply we have a gain of log lambda to some power for unity intervals. But the unity interval estimate is sharp on any compact manifold. So that's a, but we didn't construct an explicit manifold, and
Okay, thank you.
So actually I have a question about this result. So you said that it is not true for non-positive curvature, right?
Yeah.
So what fails in the proof? Like which part of the argument doesn't work?
Yeah, so in the case of, let's see. So in the case of non-positive curvature, we have compared with negative curvature. Negative curvature, we have a better control on the coefficients of the Hadamard matrix because of the comparison series. The coefficients will have exponential decay, especially for the leading term. If it is non-positive curvature, when we apply certain comparison series, it is bounded above 0, so we will not have exponential decay for large time in the coefficients of the leading terms. And so that's kind of the main difference between strictly negative curvature and non-positive curvature.
So your result is kind of more delicate than what Berar was doing. For Berar,
Say for the non-positive curvature case, and say in that case the kind of the upper bound on the exponential upper bound is sufficient in that case.
All right, so let's thank the speaker again.